Fermat's last theorem, the all-inclusive, simple, short, composite proof for x to the n times y to the n times z to the n equals x to the n times y to the n times z to the n plus zn cubed minus zn cubed. My motto? Plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. The simpleton's mathematical coat of arms. In Euclid we trust. For every triple of the form x to the n plus y to the n equals z to the n that exists, then its composite x to the n times y to the n times z to the n is uniquely identified by the identity x to the n times y to the n times z to the n equals x to the n times y to the n times z to the n plus z to the n cubed minus z to the n cubed. It is true for n equals 1 and 2, and the composite x to the n times y to the n times z to the n is reducible to solutions as the difference of two squares. It is not therefore conceivable that Fermat triples exist for n greater than 2, QED. QED proof by algebraic demonstration. 1. C equals A plus B. 2. B equals C minus A. 3. A equals C minus B. Multiply through 1 by A times B to give 4. A times B times C equals A squared times B plus A times B squared. 5. A times B times C equals A times B times C. 6. A times B times C equals C minus B times C. 7. A times B times C equals C minus B times C minus A times C. 8. A times B times C equals C minus B times C minus A times A plus B. 9. C minus B times C minus A equals C squared minus C times B minus A times C plus A times B. 10. C squared minus CB minus AC plus AB times A plus B is equal to A times B times C is equal to all the terms in brackets. 11. Group into positive and negative terms to give the composite A times B times C equal to the sum of all the positive terms minus the sum of all the negative terms, the positive terms splitting into two subgroups as shown. 12. From 4 we see that the first positive subgroup A times B squared plus A squared times B is equal to the composite A times B times C. 13. It is self-evident that the second positive subgroup C squared times B plus C squared times A rearranges to C squared times B plus A, which, when C is equal to B plus A, is then equal to C cubed. 14. We see that the sum of all the negative terms have a common factor, C, which can be taken outside the bracket, so that when we have C times that well-known algebraic identity A squared plus 2AB plus B squared, which when C equals A plus B means that C times A plus B all squared is equal to C cubed. 15. 11 therefore reduces to the composite A times B times C is equal to the composite A times B times C plus C cubed minus C cubed. When A equals x to the power n, B equals y to the power n, C equals z to the power n, then x to the n times y to the n times z to the n is equal to x to the n times y to the n times z to the n plus z to the n cubed minus z to the n cubed, QED. The next two slides, numbers 13 and 14, show that the calculated results for A, 2 to the power 7, plus 17 cubed equals 71 squared. B, 1330 cubed plus 1330 to the power 4 is equal to 14630 cubed. C, 3456 squared plus 288 cubed equals 12 to the power 7. All three of which confirm that x to the power p times y to the power q times z to the power r is equal to x to the power p times y to the power q times z to the power r plus z to the r cubed minus z to the r cubed. How's about that then for your mathematicians?